So this is the lab on Galileo's experiment. We're going to be measuring the constant acceleration due to gravity of the Earth, 9.81 meters per second squared. So if I take an object and drop it, it should accelerate downward with a constant 9.81 meters per second squared. Unfortunately, dropping it straight down means that it's going to accelerate, it's going to speed up rather quickly, and I'm not going to have the reaction time to measure with my stopwatch as it falls down. So instead we want to slow down, or we want to have a smaller acceleration, and therefore we're going to use this ramp. We'll use an inclined plane. So how is that going to help us? Well, if we look at my derivation here, if I put an object on an inclined plane, which is now at an incline of some angle theta with respect to the horizontal, that means the constant acceleration to gravity is pointing down toward the center of the Earth, but the object is now going to roll down this ramp. And as it rolls down that ramp, it's going to have some component of the acceleration, which I can calculate to be g, 9.81 meters per second squared, times the sine of that angle. So if I set the angle of my ramp at a small angle, I should get a small acceleration. If I set it at a large angle, I should get a large acceleration. And that should give us enough time with a stopwatch to measure the motion of this object going down the ramp. So what are we going to be measuring? We're actually going to be measuring the distance that it travels, x, and the time that it takes for this to roll down the ramp. We're going to set up the experiment in such a way that the initial position is going to be 0. So that's going to be 0. The initial velocity is going to be 0 because we're letting go at rest, and therefore the distance will be equal to 1/2 g times the sine of theta times the time squared. So if I make a graph of this, if I make a graph of the distance on the y-axis and 1/2 the sine of theta times the time squared on the horizontal axis, I should get nice linear data where the slope of that data is going to be equal to g, our 9.81 meters per second squared. So that's the experiment that we have here right now. I have this ramp right here, which I can use this protractor to measure the angle of the ramp with respect to the table. And then I can take my marble and I'm going to roll the marble down the ramp. And as it goes down the ramp, I'm going to measure the time. Now I'm going to measure it at a number of different distances. So I'm going to start at 1 meter and measure the time it takes to roll down the ramp. I'll go to 1.5 meters, and then I'll go to 2 meters. And so we're going to do that in triplicate. So we're going to measure the time 3 times down the ramp for each position. And then we'll change the angle of it and repeat the process. And we'll pick a third angle and then repeat that process again. So in the end, we should have about 27 data points. Okay, so let's begin. I've set this now. The initial angle is going to be at 15 degrees. So we're going to do 15 degrees, 10 degrees, and 5 degrees. So we'll start at 15 degrees, and then we'll start at 1 meter. So let me get my stopwatch, which I could also call my iPhone. Okay, so I got my stopwatch ready. So I'm going to start now at 1 meter. Ready, set, go. Okay, so at a time of 1.25 seconds. So I'm going to write that down. try it again. Oh, let me do that again. I didn't stop it in time. Try it one more time. Okay, ready, set, go. Okay, 1.11 seconds. And we'll do it a third time. Okay, ready, set, go. Okay. 1.28 seconds. That was pretty good. Pretty consistent. I'm pretty happy with those. So let's move on now to 1.5 meters. Okay, ready, set, go. Okay, so that is 1.39 seconds. And let's try it again. Ready, set, go. Okay. 1.29 seconds. And let's try it again. Ready, set, go. Okay, 1.33 seconds. Okay. Now let's go to the last distance of this angle. So that's 2 meters. And here's the 2 meter mark. Okay, ready, set, go. Okay. 1.56 seconds. And time number 2. Ready, set, go. Oh. Actually, 1.56 seconds. I don't think I could have done that if I tried. Okay, last data point at this angle. Ready, set, go. Okay. 1.48 seconds. Okay, so now what I'm going to do is I'm going to change the angle. So that was at 15 degrees. And now I'm going to change the angle to 10 degrees. So let me lower this down. There we go. Let me set this up. Okay. So now let's do 10 degrees at 1 meter. Okay, ready, set, go. Okay. 1.29 seconds. Okay, let me try it again. Ready, set, go. 1.28 seconds. And let me do the third data point. Ready, set, go. 1.26 seconds. Okay. So now let's try the distance 1.5 meters. So 1.5 meters. Okay. Ready, set, go. Okay. 1.43 seconds. Try it again. Ready, set, go. 1.54. try this one more time. Ready, set, go. 1.46 seconds. Okay. Now let's do the 2 meters. 2 meters at 10 degrees. So ready, set, go. Okay. 1.79 seconds. Do it again. Ready, set, go. Okay. 1.80 seconds. And one more data point at this angle. Ready, set, go. Okay. 1.70 seconds. Okay. So we made the measurements at 10 degrees and at 15 degrees. So let's do the last step. So let's make the measurement now at 5 degrees. Now the angle is much, much smaller. It should take a lot longer to get there. Okay. So now that's an angle of 5 degrees. And we'll start at the 1 meter mark again. And okay, ready, set, go. Okay, that was 2.03 seconds. Okay, let's do it again. At 1 meter, ready, set, go. Okay, 2.07 seconds. And ready, set, go. 1.89 seconds. Okay, so now let's move on to the 1.5 meter mark. So, ready, set, go. Okay. 2.28 seconds. Okay, the second data point. Ready, set, go. Okay. 2.18 seconds. Now, data point number 3 at 1.5 meters. Ready, set, go. Okay. 2.17 seconds. Okay, so now the last distance, 2 meters at 5 degrees. Ready, set, go. Okay. 2.53 seconds. Measurement number 2. Ready, set, go. 2.47 seconds. And last data point, 2 meters at 5 degrees. Ready, set, go. 2.47 seconds. Okay, so we've collected all of our data. So we now have data at 5 degrees, 10 degrees, 15 degrees. We've got 3 measurements at every distance, so there are 3 times. So now what you need to do is just average the 3 times for each distance at each angle, and then make 3 graphs. One graph for 5 degrees, one graph for 10 degrees, and one graph for 15 degrees. So 3 graphs, fit the graphs, and you should extract 9.81 or close enough to give us the acceleration due to gravity. Good luck.